Okay, hello, good afternoon. Thank you for introduction, and so thank you for inviting me here. I'm happy to share my idea about quantum information theories of quantum network and our directions and the recent research. So the title I put here is Building and Exploiting Quantum Networks, and I'm Joonwoo Bae from School of Electrical Engineering, KAIST. And I will start with introduction about entanglement and quantum networks, and then I will talk about our recent research, how to deal with the noise in quantum network, and then I will come to some certain applications. So this morning when I was finalizing my slides, I was thinking, so what is the good way of, or practical way of introducing quantum networks? I typed quantum network in Google, and AI already provided this solution. So this quantum entanglement and teleportation and quantum cryptography and so on and so on. Okay. So then quantum internet, the term term appeared in this paper. So it's not a real research article, but it provides a vision for the road ahead. And this paper was leveraged, I would say, by this work, solid state quantum memories by MB Center. So here they realized entanglement distillation in solid state quantum devices. But this is not the first time about quantum internet. So about 10 years before this work, there was another quantum, well, actually the first paper that mentioned quantum internet was by Jeff Kimball. That time, this paper all about atom-photon interactions. So quantum repeaters and long-distance quantum communication and quantum repeaters, how photon state can be stored in atomic ensembles and so on and so on. And why? These are the basics of, or basis for quantum internet. Then again, like 10 years back, there's a paper by, one by Charlie Bennett here, and the other by Rich Josa, also here. So both are about entanglement distillation. So nowadays we call entanglement distillation, and the first paper called purification of noisy entanglement. And for faithful quantum teleportation. And the second, they share more or less a similar idea as a quantum privacy amplification and security of quantum cryptography over noisy channels. But let me tell you what they are, okay? So actually, this is the two papers I want to celebrate for quantum networks here. Okay, so this is entangled state. We call entangled bit. So it's a unit of entanglement. And it's a very natural process that both of them, or each of them, they interact with the environment and they became a noisy state here. So it's no longer a pure state, may contain entanglement, but it contains some noise. So here I have a parameter here, f, we call fidelity. F is 1, then we have a noiseless and entangled bit. But f is larger than or smaller than 1, then we have some mixed state and noisy entanglement. And this direction, blue, is a physical process, a natural process. But the other way around is another physical process. There's no way to deterministically transform mixed state to pure state. Then this paper, two papers, one by Charlie Bennett, purification of noise entanglement and so on, and the other one, quantum privacy amplification by Rich Josa. These two papers address a solution to this problem. So it is not possible to follow the blue direction, but we slightly relax the condition. So transformation can be probabilistic. So we allow the probabilistic transformation. Then we have many copies of noisy entangled states. And out of them, we can have some clean and pure entangled bits. So it's called distillation of entanglement. And so this is possible and specifically shown by a certain protocol. So it's possible. Then the message I want to emphasize here is conceptually. So one can be completely pure out of noise, or one just needs to be noise, to be pure. So we don't need anything pure, but just collecting lots of noisy resources, and then we can extract some clean and pure resources. So yeah, it's quite intriguing. It's very nice, remarkable. And once we have this clean entangled state, entangled bits, and what can we do? And the first option, one of the first options would be quantum computation. So quantum computation can be done by not just by quantum gate, but also by entangled state. So instead of quantum gate or quantum dynamics, just collecting large size entangled states and just performing local measurement, and we can realize any quantum state transformation, which is quantum computation. So this was proposed by Rosendorf and Hans Brieger. It's called a one-way quantum computer, or nowadays we call measurement-based quantum computation. Okay, so entangled state, this pairwise entangled bits can generate useful entangled state for quantum computing. Okay, so then next about quantum communication. So two parties, say often we call Alice and Bob, they want to share this entangled state because these are sharing this maximal entangled state implies, two parties can realize quantum teleportation, so sending one qubit for free to the other in a noiseless manner. And they can also realize a secure quantum communication. Okay, let's do that. It doesn't look very difficult because it's a 2-photon or 2-qubit scenario. And yeah, so let's do that. Then the physical limitation in this is a loss. So if you use photon, okay, so then photon hardly interact with an environment, but there's a photon loss. So if we call this distance L, okay, and alpha is a parameter that takes into account all the environmental conditions, like optical fiber or atmospheric effect and so on. And then the probability that the photon arrive at this distance L drop down exponentially. So then often the practical limitation about 50 to 100 kilometers. And after that, yeah, maybe we don't get any photons from the other. Then we do have the same problem in classical communication as well. Then what is the solution for that is signal amplification. But it doesn't work for quantum scenario because no cloning theorem here. So we cannot copy quantum state, then there's a limitation in photon distribution. Then how can you realize long distance quantum communication? And then the solution is this one is called quantum repeaters. So sharing entangled state between different nodes and then performing Bell measurement or teleporting this one to the other or entanglement swapping, all these are synonyms. And by using entanglement, we can extend distance in quantum communication. So that's a great idea. And combining these two, entanglement distillation and quantum repeater, so different nodes between nodes, okay, and then parties and repeater, they realize entanglement distillation. So each node, they share clean entangled bit, entangled bit, entangled bit, and then once they are sure that, okay, we share entangled bit, then repeater applies entanglement swapping or Bell measurement or teleportation, and then after all, two parties far in distance, they can share a useful entangled state, entangled bit. Okay, so then in this way we can extend quantum communication and also quantum network as well. Okay, then just look at more carefully about the steps here. So there are two papers, there's one by Charlie Bennett and the other by Rishi Josa, and two papers, they have a different steps a little bit in the local operations, but they share the same operation in common, which is this bilateral CNAT operations. So it means take these two states, okay? So F, and this can be anything, but after Bell diagonalization and twirling and so on, then this can be diagonalized. Okay, at the moment we don't have to care, but starting from this noisy state in the first register and take the second copy here, and Alice and Bob, they perform local operations by using CNAT and perform measurement in the second register. Whenever they got the protocol works as follows. So whenever two parties get the same outcome in the second register, so I equal to J, then they accept the one in the first copy. Otherwise, they discard. So then keep doing that. So once the outcomes in the second register are identical, then we have a desired result. So we have a slightly improved fidelity F prime. Okay. So keep doing that. We can distill entanglement, and we can reach the point up to F equals 1. So this is some scheme. So suppose we are here F, then it goes up like this, and we have a F prime, and then we have a higher value, and then on so on, so on, so on. So therefore, we can reach this maximum value, which is then we reach entanglement distillation. Okay, then let's do that in reality. Then what happened? This operation is of course noisy. Then then it's also one of the difficulties to realize entanglement distillation in practice. Okay, so next part is about how to deal with this noise that happen in entanglement distillation. Actually, the paper by Prof. Duo and Hans Brigger, Ignacio Sirac, and Peter Zola, so they looked at the realistic constraint in this entanglement decision protocol, for instance, measurement in the second copy, like this, okay? So it detector contains some noise. So state is 0, but it gives sometimes 1 with some probability, also the other way around as well. So 1, then it gives outcome 0 with sometimes. If this happens, then before entanglement decision was possible, for F is between 0 and 1. Now, okay, so there's a bound which is larger than 1/2. So we lose the chance of distilling entanglement from weakly entangled state. And moreover, this bound has there's an upper bound. It means we cannot reach F equals 1. So we reach certain entanglement with this limited fidelity here. So measurement error is quite critical in this scenario. Okay, so that was the problem or analysis done in 1999. And okay, so recently we worked on that, and it's 2024. And here we provide how to purify, not entanglement, but purify noisy measurement. So the scenarios are very similar. So before entanglement distillation, we only have a noisy entanglement, and collecting noisy entanglement, we could have a pure and clean entangled bit. And here we have a noisy detector. So this noisy detector, and noisy detector all the time. And so some states are coming in, and we have use ancilla, and state interact with the ancilla by CNAT gate, and we accept the outcome whenever all the noisy detectors give the same outcome. So all zeros, all ones. Otherwise, we discard. So in this way, once the outcomes are accepted, these converge to clean detector. So we only keep using noisy detector, and after that, out of that, we can distill noiseless quantum detectors. Okay, so that's we know how to purify noise measurement and apply this one to this entanglement distillation protocol. And suppose that error rate is about 10%, which is quite high compared to, given that our current technology, 10% is almost the maximum error rate for detector. Then how many ancillas do we need in practice? The answer is surprisingly just 2 or 1. Okay, so we don't need like 10 ancillas and so on, but just 1 or 2 ancillas. We already get like 0.505, which is close to 1/2. So it's a very practical solution to noise measurement. And our idea is also conceptually the same line of the first papers about privacy amplification. So it's called also Charlie Bennett, also Ueli Maura, secret agreement by public discussion. So secret is something private to 2 parties, but 2 parties, they keep doing public discussion, which is open to even eavesdropper, but they can distill secret key. So that's the idea of this paper. And also it's related to this one, a generalized private amplification. So all these results are in the same line of conceptual equivalence of entanglement and secrecy. So I'm very happy with this result. And moreover, recent quantum computing or NISQ computing, so computing with a noisy quantum hardware, basically this can be defined as a lack of quantum error correction. So we are not able to perform, quantum circuit in a deep depths, maybe short depths, so that error is not accumulated. So we keep doing short depth quantum circuit, but we keep performing measurement and state preparation. So there will be lots of steps of measurement and state preparation. So therefore, what happens is the measurement error may propagate over different layers. But here, our method of purifying noisy measurement can be applied to this noise, the error of noisy quantum computing, and we can prevent measurement errors from propagating different layers. Okay, this is the second one. And okay, so the third part, let me be quick. So once we have a clean quantum network, then what can you do? The first one, okay, let me slightly change our approach. To see quantum advantages on over network, let me address this question. So how quantum and classical are distinct in information processing? So this is how I see advantages of quantum information processing. So maybe the first one would be Bell theorem. So Bell inequality tells there's some statistics on on measurement outcomes of quantum systems. And there's a bound by classical model is 2. And quantum model, we can go over that, 2 square root 2. But this is not a limitation dictated by relativity causality. So in physics, it's a relativity causality dictated even larger bound of 4. And we don't know any system yet to reach these 2 square root 2 and 4, but this doesn't violate any other physical principles. Okay, for that, one can ask an interesting question. So maybe in cryptography, eavesdropper is not quantum, but it's dictated by no signaling principle. It's a relativity causality. And still, quantum key distribution can achieve security. So it's by Jonathan Barrett and Hardy and Kent, and also Tonya Sin and Jisan and Masanes quite some time ago. And this is just fundamental question, but this leads to fantastic result called device-independent security of quantum key distribution. Okay, second, also I like to ask the same question about quantum state discrimination. So we have quantum state discrimination. It's a very simple thing. So non-orthogonal state cannot be perfectly discriminated. And this is actually one of the ideas for quantum key distribution also by Charlie Bennett. So 2 non-orthogonal states can be used for quantum key distribution. Okay, so it's a very simple problem. Take 2 states and give an outcome. And then from the detector, one has to guess which one is which. It's a very simple problem. It's a textbook problem. And 2000, okay, and then state discrimination has these 2 interesting properties. The first one is that in the case of Banner inequality, there's a gap between quantum and relativity causality. But in state discrimination, there's no gap. So no signaling principle can tightly dictate or determine optimal quantum state discrimination. And quantum state discrimination is conceptually also equivalent to no cloning theorem. So if a physical theory contains no cloning of state, whatever is like a generalized probability theory, but then it also implies that the theory should contain no perfect state discrimination, and vice versa. And this is, so I've explained this one in the review. And in 2018, Ralph Specken, he looked at this one, state discrimination, and compare quantum state discrimination with a non-contextual theory, which is kind of classical theory. And there's a gap between non-contextual classical theory and quantum theory in state discrimination. So this gap may be amplified and can be used for certain applications. And we looked at also the same problem, but it's a different scheme of state discrimination, or called unambiguous state discrimination, also maximum confidence discrimination. In all the scenarios, we could see the gap between non-contextual theory, which is classical, and quantum theories. And it has certainly applications for random numbers. Yeah. And well, so this is another fundamental result in a communication primitive. There could be some advantages, in particular random access code. So there's a game, like a guessing game, and at least give some preparation and both make a guess. Then we could see some gap between quantum and classical scenarios. And maybe this is the last thing, last quantum advantage I want to emphasize. So it's Peter Shor who gave the first idea about how we can get network advantages in communication. So he went to two sender and 2 receiver scenario and looked at the channel capacity. So okay, so then this is the result there, and there's one of the open problem is that okay, so 2 parties, they share non-classical correlation, can be quantum or can be post-quantum correlations. And they use this correlation to encode messages. Okay, so then there is some channel such that quantum encoding or post-quantum encoding give higher channel capacity than classical ones. So that's the result here. And so they provide different channels for that. The first channel type 1, post-quantum give advantage over quantum and classical, but there's no gap between quantum and classical. And channel type 2, there's a strict hierarchy of classical and quantum and post-quantum encodings. And then the open problem here is that for this type of channel, can there be a gap between quantum and classical channel capacities? And we have the answer here. So we found many also different kinds of network channels where we can see clearly quantum advantages over classical ones. So once we have a quantum network, I mean, we could have advantages in channel capacities. Okay, so I don't have much time to go through in detail, and it's like some ongoing project in my group. We are working on this quantum computing with the noisy hardwares. So one is ongoing project is this quantum algorithm for protein structure prediction, and the other is birth location optimizer. This is similar to Kubo problems. So connecting them, of course, there must be, we are also looking for some advantages, for instance, distributed quantum computing or scheduling problems and so on. So even, I mean, connecting noisy quantum devices, there might be some advantages. So this is something we are looking for. And okay, so that's the summary. The part one, I provide general introduction about entanglement and quantum network. And the key, the key here is that certification of entanglement is very important. So therefore, we need actually classical outcome or classical message for quantum properties. So basically, from measurement outcome, we want to be sure that there is entanglement. And the second, we provide how to purify noisy measurement to enable entanglement distillation with the noisy detectors. And this also, can be used for quantum computing. And again, although there's error correction and so on, but I believe, also in my opinion, we need more tools to deal with quantum errors to reach the point we want to have, for instance, quantum factoring or global algorithm and so on. The last one, once we have a clean quantum network, then what can we do? There are many things we can do in quantum communication scenario. Clearly, there's a gap between quantum and classical and communication protocols. And also, I want to refer to this one, the last one. Anders Winter, one day, he told me about this Winter's principle. If there's gap, then arbitrary small, then can be amplified. So it's important to find a gap between quantum and classical and find an application to amplify the gap. And then we can see clearly quantum advantages. And all this result is done by, working with my team, and here is my team. So yeah, that's all, and thanks for your attention.